So I'm a hardware person in a compiler research group, and I'm going to talk about how the work that we do in the group sort of unifies those two worlds. So modern EDA tools are pretty crazy. They're allowing us to produce really complicated pieces of hardware. We've got these GPUs that are commercially available with hundreds of millions of transistors. We've got Cerebras pumping out chips with 4 trillion transistors, and even academic communities are at a point where trillion transistor chips are possible. But I don't think I'm promoting that controversial an opinion when I say that there's still a lot of work to do for EDA tooling. And I think that that's backed up by the amount of research that we see every year trying to improve them. In PL conferences, there's new workshops that are cropping up just trying to solve this problem, and even architecture conferences are starting to publish about it, so it must be bad. So we're constantly seeing this work trying to improve correctness, consistency, and the amounts of redundancy that we have in our tool chains. So in hardware, we have these low-level languages, System Verilog and VHDL. You have some high-level languages, but ultimately, they all tend to feed down in System Verilog to be fed to a tool. And then you'll probably want to simulate your design before you tape it out. So you'll have a compiler and optimizer for that. And then you probably want to synthesize it eventually. And very often, especially in the open source world, you'll have that compiler and optimizer already implemented. And you might have that all over again for an equivalence checker and potentially even again for a formal verification tool. And we don't want this. There's a lot of unnecessary work. There's a lot of room for reinterpretation of semantics. And it's just a lot of tools for designers to have to learn their way around. In the software world, it's kind of a solved problem. They've got things like LLVM, where you have this one purpose-built representation. It's modular, so you can swap in front and back ends as you like. It's purpose-built to be easy to optimize and transform. And it's industrial strength, and it's got this really large, strong community. The only problem is it's obviously built for software. But luckily, they've produced this thing called MLAR, or the multi-level intermediate representation, and it has all of the same great advantages that we see in LLVM. But crucially, it also has this extensible dialect system where you can add your own operations and types to reason about any kind of concept you want, for example, hardware. So that's what happened in this publication my supervisor did a few years ago. There's this representation called LLHD, and it holds its way all the way through the pipeline. You use this representation for all of your optimizations, and you're lowering your languages feed directly into it, and it feeds straight into your tools. And you can even use it for your netlist IR. And eventually, that grew into this big, horrible diagram you see here called Circuit. Basically, all you need to know is it's one full EDA compiler. It has high-level synthesis support, it has HDL support, and it's built on all that MLAR infrastructure that I was talking about. It's got high and low-level dialects, so you've got your RTL down at the bottom, but also up at the top, you've got much higher-level concepts if you want to reason about something more abstract. It supports a wide range of different front and back ends and tools. And like I said, because it's built on that MLAR infrastructure, it's designed to be easily extensible. So if you have a new concept that you want to reason about, you can throw it in. And it's got a lot of industry support, which is nice to see. So the LLHD stuff I was talking about evolved into these dialects. Seek and comb is sort of your RTL of the circuit world. So seek is sequential logic, comb is combinational logic. And then down at the bottom, we have this ARC dialect, which I'll talk about next, which is a dialect designed for efficient simulation. So, like I said, we're building on all this really good software compiler infrastructure, and effectively simulation is just compiling hardware down to software. So how can we reuse all that infrastructure to make it as efficient as possible when we simulate? So normally in Circuit, before this ARC stuff, you would have used something like Verilator. And if you're starting off in Circuit, you would have started with your RTL, and then you go via System Verilog, and then C++, and then compile that down to a binary. And obviously, you're taking a detour through 2 really complicated high-level languages here that you don't really need to represent this sort of stuff. And obviously, there's a lot of bulk and bloat in the compiler that just isn't necessary. And so instead, we have this sort of gradual lowering from hardware to software, where we're moving gradually down and making the best decision you can at each of those points. So first, we prune out this sort of arbitrary module hierarchy that some designer has made up and refine it into this pure sense of state elements and combinational logic. And then gradually we inch down towards software. And it turns out that you can make pretty good decisions. So it's quite a young project, but we're the green line. Essent and Verilator are the blue lines. And as you can see, we're pretty competitive with Verilator in performance. And we're pretty solid in compile time, thanks to all that MLAR infrastructure. And as you scale up to bigger designs, the trends mostly continue, so for a small drop-off in compile time at the end. So next, like I said, Circuit has a load of high-level abstractions that are really useful, but a lot of that information is discarded when you verify it. So if you verify in Circuit currently, you have these tools, an equivalence checker and a model checker, and you'll normally get your design in RTL, and produce an SMT model and then verify that. But if you're using something like HLS, you have these high-level dialects that you might produce. So FSM represents finite state machines, Handshake represents communication through FIFOs, and those are often spat out by your HLS frontend. But all of that valuable information that really narrows down the state space of your design just gets thrown out of the window when you take this detour to RTL. So instead, we're trying to build our verification models from those high-level dialects directly to try and increase how quickly we can actually do that verification. So you'll start off with something like this. This is just an FSM. You'd obviously have that represented in your IR. And then you lower it into a much higher level mathematical model than you get from RTL. So it's something like this. This top blue bit here represents the transition on the right. And it basically says if you're in state A at a certain time with some value of your variable, then in the next clock cycle, you'll be in state B and time will be increased by 1. Then you've got this red transition that says if count equals 5 and you're in state B, then you set your variable to 0. And then this one at the bottom that basically says if count isn't 5, increment count by 1, stay in state B. And as it turns out, that really pays off. So this is performance on randomly generated FSMs compared to AVR, which won the hardware model checking competition in 2020, with the blue lines down at the bottom and then the red line up at the top. So we're doing pretty well. And it also scales really well with the length of your model checking bound, which is pretty nice to see. But like I said, these are randomly generated FSMs. So if you have any kind of EDA flows that produce explicit FSMs or use them internally, I'd be very interested to talk to you later to see how this reacts to being given actual structure for real-world examples. Finally, we've got all this really cool verification infrastructure, but what kind of hardware can we actually use to design it? Well, like I said, we're a compiler research group. And so we find ourselves looking at things like this a lot. You'll see passes like this in pretty much any mainstream compiler. But these are all rewrite patterns, basically. Rewrite patterns are incredibly commonplace in compilers. You match for some kind of pattern, and you rewrite your IR accordingly. And they take up a pretty big chunk of the runtime. So obviously, the next question is, can we accelerate them in hardware? So we start off with this MLIR pattern definition language, or PDL, that allows you to essentially define a rewrite natively within MLIR. And so you have all these rewrite patterns. Thanks to PDL, you can then unify them into one. And then the big thing is we then use that PDL to create a hardware module that can match for that pattern. And then we get that in circuit, we lower it to system Verilog, and then we put it on an FPGA. So you end up with something like this. You have this big stream of instructions that's throwing through this big pipeline of pattern matcher units, and each of those is starting at a different root operation and trying to sort of populate the tree that matches the pattern as it flows through. And as it turns out, you can fit a few thousand of these on a Xilinx FPGA, and so you can get quite a lot of parallelism out of that, and we're currently working on getting some performance numbers, which is exciting. So basically what I'm trying to say is that if you unify these EDA and compiler worlds, everyone stands to benefit across the software and compiler, the software and hardware world. So compilation can be sped up by the kinds of hardware we're producing, and then you can put that on hardware that's being designed faster, thanks to these abstractions. You can then verify faster, thanks to things like Arculator and this formal verification work, and ultimately implement faster, and then obviously that loops back around, and you can also use it to do things like compile faster. That's me, thanks.